So the goal of this section is to learn about relations, domain and range, functions, the vertical line test, function notation, and function evaluation, and implied domain of a function. Okay, so let's start out with the definition. A relation is a set of ordered pairs. So, like we have on the board, x1, y1, and x2, y2, that could be a set of ordered pairs. Okay? So a relation is a set of ordered pairs. Any set of ordered pairs automatically relates the set of first coordinates to the set of second coordinates, and these sets have special names. The domain of a relation is the set of all first coordinates. That's the domain. It's the set of all first coordinates. And the range is the set of all second coordinates. So that's your range. Okay? So, what coordinate is x1? It's in the domain, yes. What kind of coordinate is it? For the first or second? First coordinate, yes. And x2 is also first coordinate, belongs to our domain, yes. Y1 and Y2 are what kind of coordinates? Second coordinates, and they belong to our range. Very good. Okay. So a relation is a set of ordered pairs. We know the first coordinates make up a set called our domain. The second coordinates make up a set called our range. You got it. So example one. Do I need to zoom in or is this all right? What'd you say? Zoom in? What? Right here? Okay. So, for each of the following relations, determine the domain and the range. So here, S is equal to the set of all ordered pairs 0, 0, negative 5, 2, 3, 3, and 5, 3. We want to identify the domain and the range. I'll do B with you because B may look a little bit more challenging than the first one, just because of the way it's written. So I'll do B with you, and then I want you to discuss A and do A up here. Sound good? Okay. So B, we have U. Let's read it. U is equal to the set of all ordered pairs pi, comma, y. What's this bar mean? Such that. Very good. Such that y, what's that? The curly brackets mean set. So I'm asking you to remember notation we've discussed before. So you were right. This bar means, is red okay to use? Is red okay to use? That bar means such that. That means, do you remember? That's a question. No? Okay. Belongs to or is an element of. Or is an element of. You remember this notation? This is the set of rational numbers. That's the set of rational numbers. Everyone know what a rational number looks like? What does a rational number look like? I heard, So what is a natural? Say it again.
We was talking about rational numbers in Ms. Miller's class.
Yes, right. You were talking about it in Ms. Miller's class. So what does a rational number look like? Silence your phones. What does a rational number look like?
Is it just a regular number?
What kind of number? Give me an example.
Like 3. Like a fraction.
Is it just 3, or what do we know about rational numbers? They look like what? Say what? I can't hear you.
They look like repeating numbers.
Repeating numbers? What do you mean? Repeating in what way?
Like,
Do they repeat on forever? Do they stop?
like 3.333.
So is it, you asked my question, does it repeat on forever? Does it stop? Forever? How so? Like, give me an example. What are numbers that you all normally pause at whenever you see? Fractions or decimals? Why? Cause what? Sometimes what? You can't simplify them. Sometimes you can't. Sometimes you can't. Rational numbers are fractions. Rational numbers is the set of all fractions. So just a quick refresher. So this is an aside. Q is the set of all A over B such that A and B are real numbers. Can B be 0? Right. And B is not equal to 0 because we cannot divide by 0. So you may have a decimal in here, but that decimal is going to stop. It's going to terminate. That's the word we use. It's going to terminate. So it will not repeat on forever, but it'll terminate. So for example, 1/2 is the same thing as 0.50. 3/4 is the same thing as 0.75, right? So you have these are examples of rational numbers. Okay? So, are we all on the same page now? Yes? No?
Yes.
Okay. So, back to our problem. Here, we have to, for each of the following relations, determine the domain and the range. U is equal to the set of all pairs, pi comma y, such that y is a rational number. So, y can be any rational number. Infinitely many possibilities. Pi, is pi ever going to change? No, pi is what it is. So what's our domain? Pi. Very good. It's pi. I'm just going to put it in set notation because it's the set consisting of pi. Or you could just write pi, whichever one. Okay? That's our domain. Our range, what's our range? Q. Our range is Q. Why is it Q? Right, because it says y is an element of Q. So that means y can be any rational number. So we put down the set of rational numbers here. Does that make sense? Yes, no?
Yes.
Yeah, no? Oh, if there are no's, you got to ask. Okay? All right? So that's B. Do A. Take 2 minutes, do A. You can discuss it with your neighbors. You have this set of ordered pairs. Find your domain and find your range. Okay, would anyone like to come up and explain it? That's the question.
No.
No? What the heck? Why not? You not feeling me today?
We don't know what we're doing.
What you mean you don't know
We
what you're
just got
doing?
the gist of it.
You got the gist of it? What's the gist? Can somebody explain to me what's the gist of this? I'm asking, explain the gist to me.
Essentially, just finding the x's and the y's, the weights and ranges.
Say what?
For this, you're just looking
I
at
just
the
need you to
set-
speak a little louder.
For this, you're just looking at the set notations and identifying the domain and the ranges.
Yeah. So you're looking at the set notation and you're identifying the domains and the ranges, or the domain and the range. But your domain comes from what?
X's.
Your x coordinates, which are your first coordinates, yes?
Yes.
Your range comes from second or y coordinates, yeah? So that's the gist. Yeah? So when I'm saying discuss it with your neighbors, these are things you should be discussing. Okay? So, who wants to explain what our domain is? Would you like me to write while you explain? Oh, I'm patient. Say what?
Isn't domain all the x's?
Domain is all the x's? I'm with it.
So it would be 0, -5.
What do we write first?
-5. The bracket.
Oh, the what? The
Bracket.
curly bracket, yes? So go.
-5.
Talk loud where they can hear you in the back.
0.
Yep.
3
Mm-hmm.
and 5.
And 5. Any more? No, because we picked up all our first coordinates. That's our domain. Okay? What's our range?
0, 2, 3,
3.
and 3 again.
Do we have to write 3 again?
No, this is one.
No? Yes?
No,
No. Why?
because it's already.
It's already there. So we can just leave it that way. Very good. What questions do you have? Okay, excellent. So we have our domain and range. We understand what that means in set notation. So one last example, part C. We have x is equal to 3. X is equal to 3. On a graph, if x is equal to 3, what kind of line is this? Vertical, very good. Vertical. So this line is x equals 3. What is our domain? 3, very good. What is our range? Say it again. Any real number? Yes, any real number. So we write R. You can write a little better R. Any real number, because you can choose a point here. This can be 3, 5. This can be 3, -2. This can be 3, -5, and so on. So your y values can be any real number, but your x values will always be 3. So we have the set of real numbers. Okay? Another definition. A function is a relation, so it's a set of ordered pairs, in which every element of the domain is paired with exactly one element of the range. A function is a relation in which every element of the domain is paired with exactly one element of the range. Equivalently, a function is a relation in which no two distinct ordered pairs have the same first coordinate. Okay? If you have the graph of a relation, this is what's called the vertical line test. If a relation can be graphed in the Cartesian plane, the relation is a function if and only if no vertical line passes through the graph more than once.
Right.
Okay? So is x equals 3 a function? No, because if we take a vertical line, it sits right on x equals 3 and it passes through every single point. It passes more than once. Okay? So that would not be a function. So now we're going to go through some examples. We want to determine whether or not the relation is a function. If it is not a function, identify two ordered pairs with the same first coordinate. U is equal to the set consisting of ordered pairs 4, 5, 2, -3, -2, 1, and 4, -1. Is this a function? You said no? Not a function? Why?
Because the two fours.
You both are correct. It's not a function because whenever we look at 4, 5, and 4, -1, they have the same first coordinate. So not a function, we have to identify two ordered pairs with the same first coordinate. So we identify 4, 5, and 4, -1 have the same, the same x value or first coordinate. Very good. Okay. Another example. Part B, you need a second here? Yes.
So in order for it to be a vertical line test, they all have to have different x's.
In order for your function to pass the vertical line test, different x's, yes. So for example, if we have, this is to answer your question. If you have a line like that, if you take this vertical, no, that doesn't work well. If you take this vertical dotted line and take this and drag it across the green line, does it cross this green line in more than once? In more than one spot? This line, this is the line we're talking about. If we take this black line, this, think of the blue, that's just your x and y axis. That's just there. So if we look at the graph of this function, it's not this one. This is something different at this point to answer a question. But if we have this line and we take this vertical line and drag it across here, does it pass the green line in more than one spot? You said yes? Where?
It doesn't.
It doesn't? So if we take this, oops, not erase it. Let's think about this. If you have this, I hear some yeses, and so that's concerning. So let's come back to this. Excuse me. If you have this horizontal line and you take a slanted line, it's not horizontal, it's a slanted line. You take this vertical line and drag it across. Whenever you drag it, does it cross this in more than one spot?
Nope.
No. It only hits in one spot each time you move it. It only hits in one spot each time you move it. Okay? So this function here, or this graph of a line, passes the vertical line test, so it would be a function. If you have this circle and you take this line, that vertical line, it's not a function because you're dragging it across. It crosses in 2 points, in 2 spots on the same vertical line. It's not a function. Is a function, is not a function. Does that answer your question? Okay. What other questions do you have?
That made more sense.
It made more sense? Okay, good. You have to be able to take your function and put it on the coordinate plane or the XY axis and know that the XY axis is really just your foundation and the function is what you're putting on that XY plane. Okay? All right. So, part B and C. Part B, we have an upside down parabola. Is this a function or not? I heard no, I heard yes. Which one? Yes, it is a function. Why?
Vertical line test.
Good. It is a function. Passes the vertical line test. Very good. C. Is it a function? No, not a function. Why?
Fails the vertical line test.
It does not pass the vertical line test. Our instructions said that we have to identify 2 points that have the same first coordinate. So tell me the 2 points. Tell me the 2 points that have the same first coordinate.
1 and 3.
1, 3, and 1, -3. Very good. That was the instructions. So 1, 3, and 1, -3 had the same x coordinate. Okay? So let's talk about function notation. Let's talk about function notation. Function notation. This is function notation. This is read as f of x, not f parentheses x parentheses, not f times x. It's read as f of x. This is read as f of x. Note, y equals f of x is the function. So sometimes you will see f of x equals 2x minus 4. Sometimes you will see y equals 2x minus 4. This is a function. Y is the dependent variable. X is what variable? Independent variable. Good. Writing the function in function notation, instead of y, we're going to write what? So we're going to rewrite this in function using function notation. So what do we write? So what do we write? Read it. I have in part 1 how to read it. F of x. Continue. Equals what? No. We're rewriting this in function notation. Good. 2x minus 4. So f of x equals 2x minus 4. That's using function notation. Okay. So if I ask you to find f of 3, this is just extra. If I ask you to find f of 3, how would you find it? Talk loud. Say it again. Say it the other way. You're not substituting x for 3, you're substituting 3 for x, yes? You're substituting 3 for x, so you would have 2. So your solution would then be 2 times 3 minus 4, which is 6 minus 4, which is 2. Okay? So example 3. We want to rewrite the following relation as a function of x. Then evaluate the function at x equals -1. So what we want to do, we want to solve this for y. After we solve it for y, we then want to replace y with f of x. And then we want to find f of -1. Do I need to say it again? We want to solve this equation for what variable? Y. Good. Then after we solve it for y, we want to replace y with f of x. Good. And then after we do that, we want to find what? Find out what we get when x is -1, which means we want to find f of -1. Okay, so let's do that. So you can bring everything to the left or right. You don't have to bring everything, but if you choose to, this is what you would do. We really want y by itself. Subtract x squared from both sides, yes? So that gives us y equals 3. -4x squared minus x squared is what? What is it? -5x squared plus 2y. What do we do now? Subtract 2y from both sides to get what?
Y.
Negative y equals
Minus 5x
minus
squared.
5x squared. Then we want to
Or fx.
do what?
Plug in our negative one.
Nope, you're skipping some steps.
Oh, 3 minus 1.
Are we subtracting y? That's a negative y. We want it to be what? Positive y. What do we have to do to both sides? Multiply by negative 1 or divide by negative 1? Divide by negative 1. Whichever one, it's okay. Either one is okay here. So if you're dividing by negative 1 or multiplying by both sides by negative 1, this becomes y equals. What happens with the signs on the right? Yeah, so we get what? Negative 3 plus 5x squared. So I'm going to write this as 5x squared minus 3. Good. So we multiply both sides by negative 1 or we divided both sides by negative 1. So, what is going on? So we get y by itself. Now we want to replace y with f of x. So we have f of x equals 5x squared minus 3. Now we want to find f of what? Good. So we get 5 times, put in parentheses that negative 1, square it, minus 3. What's negative 1 squared? 1. So we get 5 times 1. Good, by the way. Minus 3. 5 times 1 is? 5. Good. Minus 3 is 2. That's your final answer. So we get f of negative 1 is 2. And this was the second part. I don't know what's going on, why that keeps flipping on and off. Okay? Questions? Okay? So, something that pops up. Oh, go ahead.
Is fx,
How do you read that? Is what? Look at one. Look at the part 1 where I told you how to read it. Help them out. How do you read that? F of x. So go ahead. I can't hear you. F of x will not be negative 1 all the time. And we, f of x was 5x squared minus 3. Do you mean is x always going to be negative 1? No. So for example, f of x in here, in this example above, was 2x minus 4, and I asked us to find f of 3. So we can choose different x values to evaluate our function at. What other questions do you all have? None? Okay. We saw, right? So, given the function f of x equals x squared minus 5x, I want us to evaluate the following. You'll see this type of problem again. Given the function f of x equals x squared minus 5x, I want us to evaluate the following. F of x plus h. So, the same way you found f of negative 1, you took negative 1 and substituted it into your function where you had an x. We're now going to substitute x plus h into our function where we have an x. Say it again. It's just h. It's x plus h. They're both just variables. What other questions do you have? Okay, so we are now going to take the x plus h and substitute it in here to find f of x plus h. So we get, this is equal to the quantity x plus h squared minus 5 times what? X plus h. Good. Now, x plus h quantity squared, to find that you have to use what method? Distribution, or what method? What was the question? If I ask you to find x plus h quantity squared, how do you find that? FOIL. Good. So that would be equal to the quantity x plus h times the quantity x plus h. So then you use your FOIL method. X times x is x squared plus your outer xh plus your inner hx, which is the same thing as xh. They're the same thing. Very good. You write whichever one you want. They're the same thing. And then your last. So what goes before that? Plus h squared. Good. Simplify, you get x squared plus. Good. Nope, not. I heard it on the right. 2xh, good. Plus h squared, good. And so using this aside, we've already worked everything out. So we take this, we put it right here. So this is equal to x squared plus 2xh plus h squared. What do we do with the minus 5? Distribute. What do we get? Minus what? Minus 5h. Can we do anything else? No, because there are no like terms there. So that is f of x plus h. That's f of x plus h. And so now, this you'll see again in this course because this is what's called our difference quotient. This is called our difference quotient. That's B. Oops, not through it. That's our difference quotient. And so B, using part A and using what we know our function is, I want us to find f of x plus h minus f of x over h. F of x plus h, we know, is this. This is f of x plus h. What is f of x? Very good. So it's the yellow highlighted. Very good. So this is a substitution game now. So we have x squared plus, go ahead.
Plus h squared.
Mm-hmm.
Minus 5x minus 5h.
And then we, plus or minus?
Plus.
What does this say?
Oh, minus
So minus,
x squared.
careful, we have to make sure we say the quantity so we know to put that in parentheses. Go ahead, minus x squared.
Minus 5x.
Very good. All of that over h. Okay? So now this is equal to x squared plus 2xh plus h squared minus 5x minus 5h. What do we do with that negative? Distribute it to get?
Minus x squared plus 5x.
Good. All of this over h. What happens in our numerator? Combine like terms, yeah? What happens as we look across?
X squared cancels out.
I heard two things. I heard the x squares cancel out and I heard the 5x's cancel out.
Yes.
Anything else?
What about the negative 5h?
What would happen with that?
Would cancel out.
Cancel out where?
Positive on the bottom or
Would it cancel out what?
The positive H on the bottom.
Oh, so it cannot just cancel. So are you saying, what are you saying would cancel?
Like just the negative 5.
No, we cannot get rid of the -5 because the -5 is attached to an H. So that means that -5H cannot disappear. But I think you may be onto something if you look at what's left into the numerator. So let's rewrite our numerator. So we get 2xh plus h squared minus 5h all over h. These all have what in common? H, right? So what we're going to do in our numerator, we're going to factor out an h. Once we factor out an h, that leaves us with what here? 2x plus h minus 5. All of this over h. Not 1, h, right? And so the benefit of factoring this h out is because now that you're multiplying this quantity times h, what can you do? Cancel. Yes, you can now cancel this h and this h because this quantity is being multiplied by h. So now this h can't, or those two h's cancel, leaving us with what?
2x plus h minus 5.
Very good. Very good. Okay? Yes. I need you to talk loud where everybody can hear you in the class.
Where do we get the second
What second part? There's a lot on the screen.
part? H parentheses 2x plus h minus 5.
Here? We factored out an h. All of these have, that's a good question. All of these have an h. So that means we can take, so use highlight in red. So we can take this h out. Whenever we take an h out of here, that makes that become a 1. And then we can take this h out. So that's where this h went. Good question. What other questions do you all have? What other questions do you all have?
You said which H you would take out?
We took out an h here, an h here. This is h times h. Remember, h squared is h times h. So when you take 1 out, that exponent becomes a 1. What other questions do you all have? Okay, so that's what we have there. Now let's talk about another notation. Still functions. The notation here, f, we have this f defined from A to B. This is another notation you'll see sometimes. It's another notation for functions. You'll rarely see it, but you will see it. Suppose A and B are sets. Suppose A and B are sets. F, this means, this notation, right now we're introducing notation. This notation here is read as F is defined from A to B, or F maps A to B. I'll typically say F maps A to B. This means F maps A to B. This implies that F is a function from the set A to the set B. So here, how do you read this? F maps A to B. How do we read this? No, not F implies A maps B. How do we read this? F maps A to B. F maps A to B, or F is defined from A to B. You can use either one interchangeably. A is the domain of F. A is the domain of F. B is the codomain of F. A is the domain of F. B is the codomain of F. The range of F is a subset of the set B. So for visual folks, you have A. You have B. You have F maps A to B. You can have ordered pairs. We'll go through examples now.
So kind of like a bridge, basically.
You can think of it as a bridge. Getting from A to B. You can think of it as a bridge. But everything over here maps to something over here. The way it may be set up, it may, whenever you want all of A, that's your domain. All of B is your codomain. Your range may live inside of it, but may not be all of it.
Oh, okay.
Your range may be this red subset. Your codomain is all of B, but the range may be only the red part. Okay? So, an example. We want to identify the domain, the codomain, and the range. G maps the set of integers. So Z is the set of integers. So negative numbers, positive numbers, and 0. G is a set, maps the set of integers to the set of integers. This is defined by G of X equals 3 times X. So X can be any integer. When we take any integer, our definition says what we get out of it, we have to multiply that integer by what? 3, right? So no matter what you get out of this, it's going to be a multiple of 3. Very good. So if you're picturing this, you have the set of integers, you have the set of integers, you have G. We're going to map every integer here is going to go to what we said. What did we say it was going to go to? A multiple of? But that's not going to be all of this. It's going to map to multiples of 3. Okay? So we can say this would be 3 times the integers, 3z. That would be the subset. So let me ask you this. What is our domain? The integers, good. Our domain is the integers. Remember, our domain is the A. So this is the integers. What's our codomain? Integers, yes. That's our B. That's our B. And then what's our range? It's just 3? 3z, yes. 3z, good. Very good. Very good. B. B, we're taking the positive real numbers, including 0. We're mapping that to the set of all real numbers. And we define G by G of X equals the square root of X. What is our domain? It's just 0?
It's the bracket 0,
Bracket 0, comma,
infinity,
good,
parentheses.
good. Bracket 0, comma, infinity, parentheses. What is our codomain?
All real numbers.
All real numbers. Yes, and what is our range?
Square root of X.
No, that's the function. What type of numbers can we get out of it? Say it again. What kind of real numbers? Do we get all the real numbers back? Positive real numbers. How did you get that? Say it loud.
0 to infinity.
Right. So if you're taking 0 to infinity, the positive real numbers, and you take the square root of them, you're still going to get 0 to infinity. So here, your range is bracket 0, comma, infinity. Do you need me to draw it? No? Yes? Okay. So you're taking the positive real numbers, and then, do you want to see it in set, or you want me to use a number line? A set? So you're taking the positive real numbers, and then you're mapping that to all real numbers. So that includes negative numbers and positive numbers and 0. Okay? So if we take, and that's our G. If we take a positive number and map it over here, our definition says, let me highlight. Our definition, let me use red, says g of x is equal to the square root of x. That means we can find things like the square root of 0, the square root of 1, the square root of 2, and so on. And that would map over here to give us bracket 0, comma, infinity. So that would be our range. Very good. What questions do you have? There was a so I'm trying to allow the space for you to ask it.
What did we do with the square root of x?
The square root of x means you take whatever x value, so these are your x values.
Right.
You can take your x values, and whenever you map them, or whenever you see what they map to, the x is going to map to the square root of x. So if you take g of 0 is equal to the square root of 0, which is 0. G of 1 equals the square root of 1, which is 1, and so on. So that's what lives in this set here. What other questions do you all have? Okay. All right. So do you need a second here? That's a question. Okay. Are we good? Okay. So remember, we said whenever we're looking at g of x is equal to the square root of x, it maps the positive numbers to positive numbers. So that means this x has to be greater than or equal to 0. So so our last example here, we want to determine the implied domain. Whenever we talk about the square root of a function, f of x equals here the square root of 2x plus 6. Anytime we're talking about the square root, we know what's inside has to be greater than or equal to what? We just did it in part B. The square root of x, that x has to be greater than or equal, this underneath, which is called our radicand, has to be greater than or equal to what? 0. Very good. It has to be greater than or equal to 0. Very good. So this means whenever we're finding our implied domain, we know 2x plus 6 has to be greater than or equal to 0, which means we subtract 6 from both sides to get 2x has to be greater than or equal to -6. And then what do? Very good. Divide both sides by 2 to get what? Good. X is greater than or equal to -3. So in interval notation, what is that? What is this in interval notation? Bracket, yes. Mm-hmm. Good. What goes after that? Very good. So that's our implied domain for this function. Okay? Now, B. B, we have C of x equals x minus 1 over 2 minus x. C of x equals x minus 1 over 2 minus x. Here, to find our implied domain, this is a rational function. Are we okay there? Yes or no? Okay. Rational functions, we just can't divide by what number? What can we not divide by? We can't divide by a negative? What's illegal in math for us to divide by? 0, right? Very good. We cannot divide by 0. So if we cannot divide by 0, that means this function makes sense for every number except for the number that makes this 0. So we know our implied domain here would be 2 minus x is not equal to 0. So this means if we add x to both sides, 2 cannot be, or x cannot be what? 2. X cannot be 2. So this means x can be every number except 2. How do we write that in interval notation? You need me to draw a number line? You said yes, no? Yes. So if we have this number line, we know that if we plot 2, x cannot be 2. How do we write this in interval notation? We said it can be everything except for 2. How do we write that in interval notation? I'm asking for this in interval notation. Negative infinity. Talk loud. Put what? What? Nothing goes in between? Union. Yes. Parentheses 2, comma, infinity. Parentheses. Good. That's it. That's it. What questions do you have? That's it. What questions do you have? You have a question about what? What first one? A? Part A? Go ahead. The radicand, 2x plus 6, has to be greater than or equal to 0. What's your question? So whenever you're talking about the square root, remember, can I go back to the previous page? Talking about the square root of 2x plus 6, 2x plus 6 has to be greater than or equal to 0. Yep, that's the connection. Very good. That's the connection there. What questions do you have? What other questions do you all have? You had enough for today? Y'all give me blank looks. I can't read them. I can read them, but I need to hear it. Okay.